In this example, we are going to talk about inference in simple linear regression. So for example, we have the data. This is weight, and this is the length. Is there any linear relationship? We know we can plot the scatter plot. We can put a line, which is the least squared line. And does this mean there is a linear relationship? We need to do the hypothesis testing. So now this is x, that's the explanatory variable, y, that's the response variable. So first we show how we can manually do the inference. So what we need to calculate, so what is x bar, what is y bar? So x bar, y bar, let's just use the Excel, take the average, that's the mean. And what's the sample standard deviation? We use the Excel function, the standard deviation of the sample. We calculate the sample standard deviation. We also need to find out, this is the sum squared. Okay, that's x minus x bar and squared, okay, for this one, and add them together. That's sum squared x and sum squared y. Okay, that's y. So that's the deviation from the average. So each individual value, and then we add them together. Squared, because sum squared y, and sum squared xy. That's just the x minus x bar, and then multiply y minus y bar. So we add them together. That's the sum squared xy. So we use it because we need this in the formulas. You see, this is the formula we used. So we need to manually calculate them. Certainly, R, we know that's the coefficient. That's a correlation coefficient. So for this one, we know we have the formula we can use. See, this is 0.9. So that's, yeah, positive, quite a strong positive correlation, because we know the correlation coefficient is closer to -1 and +1. That means more strong linear relationship. Close to 0 means weak linear relationship. So this one is quite a strong linear relationship. And we also can calculate R squared, so which is just correlation coefficient squared. So what does this mean? So this also called the coefficient of determination. So this means 94.9% of the variance is explained by this regression model. So we also call this goodness of fit test. So how good your model fit the data. So this is pretty, yeah, it's very good. Okay. So next we need to find out the model, the least squared line. So the slope, that's R, and then multiply the standard deviation of x over standard deviation of y. So this is the slope, and then we have the formula for the intercept. Okay, so this is y bar minus x bar multiply the slope. So this gives us the model. So the model is beta 0 hat. So this is the intercept plus beta 1 x, beta 1, that's the slope, beta 1 hat. So why we say beta hat? Because hat means it's from the sample. Okay, just this sample gave us describe the relationship just based on this sample. The least square is from sample, so we call beta hat. So next is we need to find out. So another way to answer the question, does the data follow the linear relationship? So we need to do the hypothesis testing. So for this hypothesis testing, we learned the non-hypothesis, there's no linear relationship, which means slope 0. Okay. So alternative one, there is linear relationship, so slope, so it's not equal to 0. So for the hypothesis testing, we need to know what's the test statistic. So here is the t-value. Okay? So the t-value is the test statistic that's based on this formula. So we calculate this is slope minus 0 and divided by, this is the standard deviation of beta 1 hat. Okay? So that's mean squared error part over the sum squared x. So just this is, we calculate t-value here. It's just based on this formula. So once we have the t-value, we find out the p-value. Okay? So that's the t-distribution. We have the t-value 18.358. And then we need to know the degree of freedom. That's n minus 2. So in this case, n, that's the how many pairs of the points. So in this case, we have the sample size 20, so 20 minus 2, that's the degree of freedom. And we calculate the p-value. It's 0, it's almost 0, it's 0, okay? So since p-value equal to 0, our non-hypothesis is the slope is 0. So we reject, we have enough evidence to reject the non-hypothesis. In other words, we have enough evidence to support alternative hypothesis. So the slope is not 0. So there is a linear relationship between x and y. So this is the conclusion. Hypothesis testing. So here we not only learned we can build the least square line, we also can evaluate, okay, can do the inference on the coefficient. We also can build confidence interval. So because we know there is a linear relationship, there's a linear relation, the beta 1. Okay? But we calculate only based on these 20, the 20 pairs of data. We calculate the beta 1 hat. That's just one sample calculate. So if you have another, x and y from the population, we can have another sample. So may have another beta 1 hat. But we can, based on this just one sample, we can create a confidence interval because this beta 1 hat follow normal distribution. Okay? The center is the population beta 1. So we build a confidence interval just based on, so this is how we build confidence interval. So we know this is the sample statistic beta 1 hat plus minus t-value multiply the standard deviation of beta 1 hat. Okay. So the t-value, we just check the table, see this is a degree freedom 20 minus 2, 95%. Confidence interval, so alpha 0.05. So we follow what we learned before, so we can find out what's the t-value. This is based on the alpha, so we can find out the t-value, and then we can calculate the standard deviation, the error part, plus minus part. So we can find out the confidence interval. So next is, we know we have this beta 0 hat, beta 1 hat. That's just the estimate of the coefficient from our one sample size 20. If x equal to 1.4, what is the y value? So this y value, we can calculate the y hat. Okay? So we also can build a confidence interval for y hat. We call prediction interval. Okay? So when x equal to 1.4, what's that interval for the true y? Okay? So this is the formula we use. Okay? The true y, this beta 0 hat plus beta 1 hat multiply the x value. Okay? That's the y hat. And then plus minus an error part. So this is the formula. We just follow the formula to calculate the error part. Give an interval. So this is called the inference on this predicted value. So next, we are going to talk about how we use Excel to generate the least square line and to do the inference on the least square, this coefficient, slope, and intercept. So under data analysis, there is one function called regression. We click regression, and then we have the input y range. So this is y, the response variable, and then the input x, that's the explanatory variable. This is the range x. So we include the name of the column, and then we put check labels. That means the first row is the name of the column. And we want to build the confidence interval, confidence level default 95%. So we check this one. And then we can have the output. You can either just by default new worksheet or you all output in the same sheet. So by default we generate a new worksheet. And then we check the residuals, residual plots, 9-fit plots, and normal probability plots. For all this, used to check the assumptions. So does the linear regression is appropriate model to use here? We have the assumptions. So now this is the result. So here calculate the value of R. That's the correlation coefficient. This is the correlation coefficient. This is R squared. It's just the coefficient squared, standard error point. And it provides a ANOVA table. So we know ANOVA, that's also another test, F test. Okay? They test the variance. So they test the ratio of the mean squared, this mean squared error, and versus the mean squared, the model part, the regression model part. So if this p-value, the F ratio is very large, okay, or the p-value very small, that means this model, okay, the regression, is really make the difference, is significant. So that's also verify your model is valid. So here is the coefficient, inference on the coefficients. So this is the intercept. This is the slope. So see, this is calculate the t value, which is same as, we already did our manually calculate the t value. 18.358. So we can do the same thing, calculate t value for the intercept. So we're not covered here. We more focus on interested in there is a slope or not. So this is the t statistic. This is the p-value. So based on p-value is very small, see almost 0. So that means there is a linear relationship. So we calculate it's just the confidence interval for the slope. Okay. So now there is the important assumptions for the linear regression model. So the residual should be normal, independent, and constant variance. So you see the residual, if you plot the residual, it should be, shouldn't have any pattern. And also we can put the residual data into JMP, and then we create this probability plot or quantile plot. It should be a straight line, shows the residual is normal, like the error part is normal and no pattern. So like this one shows the residual versus the weight x, there's no pattern here. Okay. if there is a pattern, that means there's some other factors involved, but your model cannot explain it. So here just shows this is the line, the least square line, and this blue ones, that's the empirical data, your sample data. So it looks matched well. Okay, so this is the Excel output. What we need to know, for example, how to, if I gave some value, like the fill in the blank for the ANOVA table, or fill in the blank for this, the inference on the slope. Okay, you should be able to. So next, about the JMP, how to use JMP to generate this inference on the linear regression model. So analysis the linear regression model. We can copy the data and then to put into JMP, we create the new data table. We also need to make sure these both, you look at the icon here, this blue triangle, that means both data are numerical or quantitative. We build linear regression model, X and Y both should be a quantitative value. And then we go to analyze, just fit model. So automatically it will pick the regression model. So Y, this is X. You click run model. So this is the output. We scroll down, we see it's also give us, so what's the R square, which is, that's the coefficient of the correlation. This is R squared. Yeah, this is all same as Excel output. Analysis of variance ANOVA table. And also parameter estimates, the intercept and the weight, the slope. So what's this is the slope, the beta 1 hat, and what's the standard error part, okay? And what's the t-value, and what's the corresponding p-value. So if we have the it also tests the hypothesis residual by predicted plot. There's no pattern here. So residual, that's the error part. If we like to see what's that's the residual normal or not, in JMP, there's no normal quantile plot automatically give it to you. You need to save the residual. We check this one. The red triangle, that's the menu. And then we can see save columns. We save the residuals. So say there's another column called residual here. That's the error part. So we can generate test the normality for this one. As we learned. Okay. So we can generate normal quantile plot. See, it's not that close, but mostly close to the straight line and no points out of these limits. So we will see the residual approximately normal. So this is how you test the assumptions in JMP.